In this video, I'll show you how to create a thermal model of an item of electronic equipment using mechanical and electronic CAD data in 6SigmaET. The thermal simulation will be used to validate and improve the thermal design of the equipment. First, we'll import a 3D CAD model of the enclosure. STL CAD files can be directly imported into 6SigmaET. All the detail from the CAD models is retained. The solid definition first needs to be separated into component parts, then the parts are moved into the solution domain. The material of each of the enclosure parts needs to be specified. The properties of multiple objects can all be changed at the same time. 6SigmaET has a library of material properties, both metal and non-metal. The case is made from aluminium and the screws are made from steel. The configuration of the enclosure is now complete. The case is set to be displayed as wireframe, so we can easily place the objects inside the enclosure. The next step is to import the design of the PCB. The EDA file formats IDX, IDF and XFL can all be imported directly into 6SigmaET. In this case, the PCB design is imported using the IDF file format. The PCB components are placed onto the PCB. The PCB is moved into the correct position in the enclosure. Notice that the components placed on the board move with the PCB. PCB traces can be imported and modelled in the thermal simulation. Trace information is imported directly onto the PCB using the IDX format. You can see the PCB traces on the surface of the PCB. The next stage is to set the power dissipation of each of the components on the PCB. The simplest way to do this is to import a list of component powers from a spreadsheet. The component powers are matched to each component. A pre-configured plot graphically shows the power dissipation of each of the components. There are 3 components on the top of the board with a high power dissipation, and 3 components on the bottom of the board. A pin-fin heatsink is added to 3 of the components with a high power dissipation. The heatsink object can be easily configured to match the design. Heatsinks will automatically be placed correctly on top of these components. The heatsinks have 6 pins through and 6 pins across, and have a height of 12 mm. Now we'll look at the components on the underside of the board. A thermal interface pad is added to each of the 3 components on the PCB, so that the heat from these components can be transferred to the equipment case. The thickness of the TIM is defined. Its thermal specification can be found in the library. You can see there is now a conduction path between the component and the enclosure. The next step is to set the thermal limits of the components in the model. All the components in the model can be found using the powerful Find tool, and the thermal limit can be set for all components at once. The model is now ready to be solved and analysed. When Predict Temperature is selected, a grid will automatically be generated and the model will be solved by the powerful parallel solver. We will now look at the results. The result we're going to view first is the component overheat plot. This shows which components are operating close to or over the maximum operating temperature. You can see that 7 components are overheating or borderline overheating. The thermal management of this equipment needs to be improved. The PCB surface temperature plot shows that heat from the components in the top left of the PCB is not being effectively dissipated away from the board. The version tree allows you to experiment with different versions of the model in the same project, so you can identify the optimum solution to a problem. One possible solution is to add additional heat sinks to the other components on the board. That way, all the major components have a heatsink fitted. The model has been solved, so we can again look at the component overheat plot. And as you can see, there are still several components that are overheating. If we look at the PCB surface temperature plot, we can see there's still a very hot region around the components. There are no vents in the enclosure, so there's no air entering the enclosure. Transferring the heat to the still air is not very effective, so adding additional heat sinks is not very effective. An alternative solution is to add a large thermal interface pad underneath the board. This will provide a heat conduction path between the board and the enclosure. If we look again at the surface temperature plot, you can see that the board temperature is much more uniform and the maximum board temperature is significantly lower. The heat is being effectively dissipated to the case. The overheat plot shows that with the addition of the thermal pad, all components will operate below the maximum operating temperature. In the last few minutes, I've shown you how you can create a thermal model of a piece of electronic equipment using mechanical and electronic CAD data in 6SigmaET. The results from the simulation we use to identify a thermal issue and find a solution to the problem. For more information about 6SigmaET, please visit www.6SigmaET.info.